we actually scale the EC2 instances in the backend if we're using it. So we have multiple ways of doing it. We can use an auto-scaling group scaling. And so we scale our ASG, for example, based on CPU utilization. And then we can add CPU.
Hey everybody, this is Andrew Brown and
Peace.
Hey everybody, this is Andrew Brown and welcome to the AWS Cloud Project Bootcamp. As we continue on with week 2 of our required homework. So there are a few things that we want to achieve. We did honeycomb in the live stream. It says roll bar test.
The EC2 instance over time if the CPU skyrockets. Or we can use the newer and more advanced feature called the ECS Cluster Capacity Provider that we've seen before in the hands-on. And with this one, the capacity provider is very smart. And as soon as you lack capacity to launch new tasks, it's going to automatically scale your ASG. So the capacity provider is paired with the autoscaling group. And then when you're missing RAM or CPU, there you go, EC2 instances are created. And so the second option is the smarter way of doing things. So if you had to choose between autoscaling group scaling and ECS cluster capacity provider, please use ECS cluster capacity provider for your EC2 launch type. So let's have a look at this service. So we have a service A with 2 tasks, and we have CPU usage, and it's going to be auto-scaled by the AWS application autoscaling. But let's assume we have more users, and therefore your CPU usage goes really up. Then your CloudWatch metric, which monitors the CPU usage at the ECS service level, again, is going to trigger a CloudWatch alarm, which will trigger a scaling activity in your autoscaling for your ECS service. The desired capacity will be created. And optionally, if this service is running on the EC2 launch type, can help you scale your ECS cluster backed by EC2 instances. Okay, that's it. I hope you liked it, and I will see you in the next lecture. Now let's talk about a few solution architectures you can encounter with Amazon ECS. So the first one are ECS tasks invoked by Event Bridge. So for example, say we have an Amazon ECS cluster, it's backed by Fargate, and with an S3 bucket. Our users are going to upload objects into our S3 bucket, and these S3 buckets can be, for example, integrated with Amazon Event Bridge to send all the events to it. And Amazon Event Bridge can have a rule to run ECS tasks on the go. Now your ECS tasks are going to be created. They will have an ECS task role associated with them. And from the task itself, what it can do is that it can get the objects, process it, and then send the results into Amazon DynamoDB. And that is thanks to the fact that we have an ECS task role associated with it. And so effectively here, what we've done is that we've created a serverless architecture to process images or to process objects from your S3 buckets using a Docker container. And that is using Amazon Event Bridge, ECS in the Fargate. target mode, as well as an ECS task role to talk to Amazon S3 and Amazon DynamoDB. Another architecture using, again, EventBridge is to use an EventBridge schedule. So we have an Amazon ECS cluster backed by Fargate and Amazon EventBridge, and we schedule a rule to be triggered every 1 hour. Now this rule is going to run ECS tasks for us in Fargate, and so that means that every 1 hour a new task will be created in our Fargate cluster. And the task can do whatever we want. For example, we can create an ECS task role with access to Amazon S3, and therefore our task, our Docker container, our program, can, for example, do every 1 hour some batch processing against some files in Amazon S3. And again, all of that architecture is fully serverless. A last example is using an SQS queue. So we could have a service on ECS with 2 ECS tasks, and messages are being sent into an SQS queue, and the service itself is pulling from messages from the SQS queue and processing them. We can enable ECS service autoscaling on top of this service. That means that, for example, the more messages we have in our SQS queue, the more tasks we're going to have into our ECS service thanks to autoscaling. Another integration is when you want to use EventBridge to actually intercept events from within your ECS cluster. So for example, say you wanted to react to tasks being exited. In that case, any task exiting or starting in your ECS cluster can be triggered as an event in EventBridge, and it will look like this. For example, the ECS task state change for stopped and the stop reason. Then from there, for example, we could alert an SNS topic and send emails to your administrators. So bottom line, EventBridge does allow you to understand the life cycle of your containers in your ECS cluster. Okay, so that's it for this lecture. I hope you liked it, and I will see you in the next lecture. So let's make sure to destroy everything before we're done. So first, we need to stop the service. So to stop the service, make sure you have 0 tasks running. If not, you update the service and you set the desired task to 0. And then you can click on delete service, type in delete, and this will delete the service. Now, when you delete the service, this is actually going to go into a service called CloudFormation. And CloudFormation is going to take its time to delete the entire stack that it created. And so part of the things it's going to delete is the ECS service, but also your load balancer listener, your load balancer itself, the security group, and the target groups. So this can take a little bit of time, and we need to wait for everything to be deleted. And when the service is fully deleted, then you can go and delete this cluster. So for this, you just click on delete cluster, and it's going to delete the demo cluster. And we can do this right now. And again, this is going to start something in CloudFormation to delete the infrastructure of the ECS cluster. So that includes the capacity provider, the autoscaling group that we have created, the cluster, and the launch template. So this is very good. Finally, for your task definition, you can leave them as is. They don't cost you any money. They're just definitions. But if you wanted to, you could also click on one of them and deregister, do action and deregister the task definition itself. So that's it. I hope you liked it, and I will see you in the next lecture. Okay, so let's do a short intro to Amazon ECR. So Amazon ECR stands for Elastic Container Registry, and it's used to store and manage Docker images on AWS. So far we've been using online repositories such as Docker Hub, but we can also store our own images on Amazon ECR. And actually, you have two options for ECR. You can store images privately just for your accounts or your own accounts with an S, or you can use a public repository and publish to the Amazon ECR public gallery. Now, ECR is fully integrated with Amazon ECS, which is great, and your images are behind the scenes stored by Amazon S3. So your ECR repository may contain different Docker images, and then your ECS cluster, and for example, an EC2 instance on your ECS cluster may want to pull these images. So to do so, well, we're going to assign an IAM role to our EC2 instance, and this IAM role will allow our instance to pull Docker images. So, of course, all access to ECR is protected by IAM. That includes that if you have a permission error on ECR, have a look at your policies. And then your containers are going to be started on your EC2 instance after they are pulled by your EC2 instance. And this is how ECS and ECR work together. Now, Amazon ECR is great because on top of being a repository, it supports image vulnerability scanning, versioning, image tags, and image lifecycle. So overall, anytime you see storing Docker images, think ECR, and that should be it for you at the exam. All right, I hope you liked it, and I will see you in the next lecture. So let's talk about the other way to run containers onto AWS, and this is using Amazon EKS. So Amazon EKS stands for Amazon Elastic Kubernetes Service. So it is a way, as the name indicates, to launch a managed Kubernetes cluster onto AWS. So what is Kubernetes? Well, this is the blue logo you see in the top right corner of the screen. Kubernetes is an open source system for automatic deployment, scaling, and management of containerized, usually Docker, applications. So it is an alternative to ECS, which has a similar goal, which is to run your containers, but a very different API. The idea is that ECS is definitely not open source, whereas Kubernetes is open source and used by many different cloud providers, which gives you some sort of standardization. So EKS supports two launch modes again, the EC2 launch mode if you want to deploy worker mode like EC2 instances, or the Fargate mode if you wanted to deploy serverless containers in an EKS cluster. So the use case for using EKS is that your company is already using Kubernetes on premises or already using Kubernetes in another cloud, or they just want to use the Kubernetes API and they want to use AWS to manage the Kubernetes cluster, then they would use Amazon EKS. So again, Kubernetes, from an exam perspective, is cloud agnostic. It can be used into any cloud, such as Azure, Google Cloud, and so on. And so that means that if you're trying to migrate between clouds or your containers, using Amazon EKS may be a much more simple solution. So in terms of diagram, this is what it looks like. So we have a VPC, 3 AZ, separated into public subnets and private subnets. And so you would create EKS worker nodes. They would be EC2 instances, for example. And each of these nodes will be running EKS pods. So they're very similar to ECS tasks, but from a naming perspective, anytime you see pods, it relates to Amazon Kubernetes. Okay? So we have EKS pods, and they're running onto EKS nodes. And so these nodes can be managed by an auto-scaling group. Now, very similarly to ECS, if we wanted to expose a EKS service, a Kubernetes service, we could set up a private load balancer or a public load balancer to talk to the web. So let's summarize the different node types that exist for Amazon EKS. So you have the managed node groups, and this is AWS that will create and manage nodes, so EC2 instances, for you. And these nodes are part of an auto-scaling group managed by the EKS service itself, and you have support for on-demand and spot instances. You can also choose, if you wanted to self-manage nodes. This is if you want to have more customizations and more control. So in that case, you need to create the nodes yourself, and then you need to register them to an EKS cluster, and then you manage your own nodes as part of an ASG. You can still use the pre-built Amazon EKS optimized AMI for this, which saves you a bit of time, or you can build your own AMI, which is more complicated. This supports as well the on-demand and the spot instances. And finally, if you don't want to see any nodes that supports the Fargate mode, in which there is no maintenance required, and no nodes are managed at all. You can just run containers on top of Amazon EKS. Now you can attach data volumes to your Amazon EKS cluster. For this, you need to specify a storage class manifest on your EKS cluster, and this leverages something called the Container Storage Interface CSI compliant driver. So keywords to look out for at the exam, and you have support for Amazon EBS, you have support for Amazon EFS, and this is the only type of storage class that works with Fargate. You have Amazon FSX for Lustre and Amazon FSX for NetApp on tap. So that's it for Amazon EKS. I hope you liked it, and I will see you in the next lecture. So I want to show you a quick hands-on for Amazon EKS, but this is completely out of the free tier. So if you do decide to do it, it's going to cost you quite a bit of money. So I just suggest you just watch what I'm doing just to understand a bit better the Kubernetes per service from AWS. So we're going to create a new cluster on AWS. So I use demo EKS as a name. I can select a Kubernetes version. I will use the default. And then we need to have a service role to manage everything. So to create this role, I need to follow the instructions from the EKS user guide. So I go to IAM, and then I will have to create a role for EKS, and then I will need to add the EKS cluster role. So let's do this. We're going to go to roles, create a role. This is for a service. This is for the EKS service. Here we go. And we'll do EKS cluster to allow access to other services that are operated by our cluster. So here we go. We're good. Next. Then the permission is selected already. And the role name is EKS cluster role. Let's create this role. Invalid name. So let's just remove the first space in the beginning. And now the role is being created. Okay, so let's refresh this and we can find this role right here. Now, do we want to encrypt our secrets with KMS? For now, I'm not going to do it, but this is a possibility for security. Then where do we want to deploy our cluster? So we have a VPC and subnet. So this is so we are highly available. Then security groups we want out of this. So we could select, for example, the default security group, and then we choose the IPv4 type of services. Then the cluster endpoint access is going to be public so that we can access it from our computer. Do we want any networking add-ons? So we'll just use the default again and the default for proxy and DNS. So as you can see, these are like a lot of configuration, and EKS should be its own course, to be honest. I just want to run through the options so you can understand what's happening. Then we can configure logging for the control plane. I'm not going to do it. And then we review the settings. So we have set up security groups, networking, cluster API access to public, and we are good to go. So let's create this. And what this is going to do is that it's going to create the cluster itself, and then we'll have to create the nodes for the cluster. So my cluster is now created, and the next step is to provision compute capacity for your cluster by adding a managed node group or creating a Fargate profile. So we've seen this in the overview, and that's just what I wanted to show you. So if we go into the resources, this is where all your Kubernetes resources are going to be managed. And this is some Kubernetes specific knowledge, okay? But this is where you would have it for the Kubernetes experts. Then in compute, this is where we can add node groups. So if I go into node groups, I can add a node group here. I'll call this one demo node group. You would need to create an IAM role for this node group. So we go into the IAM console. And then we create a new role. And this role is for the EC2 instances that are part of my managed node group. So I will just use EC2. And then I will search for policies. I will type EKS. And you want an Amazon EKS worker node policy added in it. So let's click on next. And for this, I will enter, and it's somewhere in documentation. So I will enter the Amazon EKS node role. And actually, there's add permissions for this. And then we need to also add the Amazon EC2 container registry read-only policy in this. So let's go back. In here, we're going to edit permissions and add one more thing, the Amazon EC2 container registry. So let's look for this. Here we go. It's here. Next. And we're good to go. Let's create this role. So let's make sure it doesn't start with a space. Here we go. The role is created. And now I'm able to go in here, refresh this, and I will find the Amazon EKS node role. Great. Then do we want to have a launch template for our EC2 instances? We can specify one, but I will leave this unticked. And then click on next. what type of node group do we want? So Amazon Linux 2 is great. Do we want on-demand or spot instances? What type of instances do we want? So do we want T3 medium, T3 micro, whatever you want? What is the disk size? What is the node scaling configuration? So how many nodes in your node groups do you want? So this is the settings for the auto scaling group. And then what is the node group update? So when you do update, how many nodes can you tolerate to be down? So click on next. What subnets do you want access to? And then when we're good to go, we create this managed node group. And so to show you this, this is the way to deploy EC2 instances for your Amazon EKS cluster, but they are entirely managed by AWS, which makes it very easy. And the other way to create nodes in here, so we go one level up, we go back into compute. The other way to create nodes, except from this node group, is actually to have Fargate. And Fargate allows you not to provision EC2 instances. And so we would have with the setup to go and add a Fargate profile. Now we're not going to do this. I just wanted to show you the options for node groups for Fargate profiles. I actually don't need this one, so I'll delete it when it's finished creating. And the last option I want to show you is around add-ons. So if we wanted to actually use EBS volumes, we can install add-ons, and one of them is the Amazon EBS CSI driver. And this will allow us to leverage EBS for our Amazon EKS cluster. And there will be a CSI driver also for FSX, EFS, and so on. Okay, so this is all the options I want to show you. Kubernetes requires its own knowledge, to be honest, and it's very, very difficult and requires a full course on it. So what I'm going to do now is just go ahead and delete this cluster. So for this, I'll just type demo EKS, and this will be it. All I wanted to show you was how to create an EKS cluster. And to delete it, I first need to delete the node groups. I will skip that from the video. So that's it for this lecture. I hope you liked it, and I will see you in the next lecture. So now let's talk about the AWS App Runner service. It's a fully managed service that makes it easy to deploy web applications and APIs at scale. And with this, anyone can deploy to AWS. You don't need to know anything about infrastructure for containers or your source code or whatever you want. So the idea is that you start with your source code or a Docker container image, and then you're going to configure the settings, such as how many vCPUs you want, how much memory you want for your containers, if you want auto scaling, and a few health checks. So some basic settings to define your web application or your API. And then automatically, that's it. It will start building and deploying the web app using the app runner service. So the container will be created and deployed, and then your API or your web app is deployed and you can access it right away using a URL. And so as you can see, there was no knowledge whatsoever of what goes on underneath. Underneath, of course, it uses the AWS services, but as a user, you just don't know about it. So it's very quick. So with App Runner, you get a lot of goodness. You get automatic scaling, it's highly available, you get load balancing, you get encryption, and your application, your container, can also get access to your VPC. That means that you can connect to your databases, your cache, as well as your message queue services. So the use case for this is to very quickly deploy web apps API, microservices, and do rapid production deployment with best practices, all using the AWS App Runner service. It's a very simple service. It does very simple things, but it's very powerful. Okay, that's it. I hope you liked it, and I will see you in the next lecture. Okay, so I want to show you how AWS App Runner works, but this is not part of the free tier. So if you do decide to follow along with me, just know you're going to pay some money for vCPU and per gigabyte, okay? So let's go and create an App Runner service. So first we have to say the source of our deployment. Is it part of a container registry, or is it part of a source code that we can connect, for example, from GitHub, okay? We are going to use the container registry. Now it can either be Amazon ECR if it's an internal private Docker container you have in your infrastructure, or Amazon ECR public if you wanted to deploy a public image. And we're going to do this. We're going to go into the Amazon ECR public gallery website, and I'm going to do HTTPD just to deploy a very simple HTTP server to do basically nothing but show you how to deploy an HTTPD server. So I'm going to just copy this right now, copy this address and paste it here. Okay. Next, what is the deployment settings? So whether or not we want to manually deploy our application or automatically. So if we were enabled with a source code repo or Amazon ECR, we could do automatic, but we are doing something manual right now, which is fine. So let's click on next. Then I'll call it demo HTTP. We choose how many vCPUs we want and how much memory we want. So 1 vCPU and 2 gigabytes is fine. This is the lowest I can get. We can pass environment variables. We can configure the port of our service. So if we go in here and we have a look at the documentation, we can probably find that the port of it is port 80 of our image. So we're going to use port 80, and I'm pretty quick because you don't need to know why exactly, but here we go. So it's port 80. Then do we want to configure auto scaling? So do we want to have the default configuration from 1 instance to 25 instances? And what is the concurrency? So with this scaling, we'll have 100 requests, concurrent requests per instance, which is great. Or you can use your custom configuration or add a new one, okay? Then you can do health checks. So do you want to perform health checks on your application to make sure it's healthy? So we can leave this as is. Security, if you want your containers to have an instance role. Networking, if you wanted to deploy into your custom VPC, but for now we'll use a public access type of access. And we want tracing with AWS X-Ray. So for now, I'll keep everything as default and press next. So we verify the settings. So we use a public HTTPD image, and then the port is on port 80. So this is pretty simple because we just specified one container, and then we just click on create and deploy. And behind the scenes, App Runner is actually going to deploy an auto scaling group. It's going to deploy scaling triggers. It's going to deploy most likely like Fargate containers. It's going to deploy a load balancer. It's going to give us a domain and so on. So it's quite handy. And from this one interface, I can get access to my logs, my activity, my metrics, my observability, my configuration, as well as connect any custom domain. So it's a very powerful all-in-one service to deploy containers in a production fashion on AWS. And I really like it. So it took a bit of time, but my service is now created. And if I click on this, I'm able to access my default domain, and it just says it works, which is the message that is displayed when you have deployed HTTPD correctly. So that's good news, it works. And if we have a look at it, we can look at the event log into where to see if everything was being deployed, the health checks and so on. And that's about it. It's as simple as that. And if we were to have a lot of concurrent requests on this website, then automatically it would scale, which is quite nice. So that's it really. I find App Runner incredibly easy to use. So now we can just delete this application, which type delete, and we're done. So that's it for this lecture. I hope you liked it, and I will see you in the next lecture. Okay, so let's discuss now what is serverless. So serverless is something new, and the developers, when you use serverless services, you don't have to manage servers anymore. So it's not that you don't have servers anymore, it's just that you don't manage them. You just deploy code. And originally, you just deployed functions. So initially, serverless meant function as a service, or FaaS. But now, serverless means a lot more. So in the beginning, serverless was pioneered by AWS Lambda that we'll see in this section, but now also includes anything that is remotely managed. So databases, messaging, storage, as long as you don't provision servers. So serverless doesn't mean there are no servers, it just means you don't see them or you don't provision them. So if we drill down into what serverless means in AWS, we have our users, and they would get, for example, static content from our S3 bucket, delivered as a website, or CloudFront plus S3. Then we would log in with Cognito. This is where our users would have their identity stored, and they would invoke your REST API through the API gateway. The API gateway would invoke Lambda functions, and Lambda functions would store and retrieve data from DynamoDB. So this is just an example. This section is going to be dedicated to learning a lot of things around Lambda, DynamoDB, API Gateway, Cognito, and so on. But so it's just to give you a reference architecture for serverless applications. So in AWS, it's Lambda, DynamoDB, Cognito, API Gateway, Amazon S3, but also things we've already seen, such as SNS and SQS. Yes, indeed, we did not manage any servers for SQS and SNS, and it was scaling on its own, so that fits the serverless use case. Kinesis Data Firehose, because again, it scales based on the throughput you have, you just pay for what you use, and you don't provision servers. Aurora Serverless, when your Aurora database scales on demand without you managing servers. Step Functions, and Fargate, because Fargate was a serverless function of ECS, where we didn't provision the infrastructure to run our Docker containers. So hopefully that's a short and sweet introduction to serverless. In the next lecture, we'll be starting with AWS Lambda, and it will be a lot of content to learn, but the exam does test you heavily on your serverless knowledge, so let's get started. So what is AWS Lambda and why is it helpful for us? So let's take an example. We are going to start with Amazon EC2, and Amazon EC2, as we know, they're virtual servers in the cloud, and we have to provision them, so we are limited by the amount of memory and CPU we're going to provision. They have to be continuously running. I mean, we can optimize them by starting them and stopping them efficiently, but otherwise they run continuously regardless of if something is happening or not on your instance. And if you want to scale, you can use auto-scaling groups, but that means that you need to do something to automatically add and remove servers. Now, this is one way of doing things, and it has worked great, but then there is AWS Lambda. So with Lambda, these are virtual functions, no servers to manage. So that means that we just provision the code and the functions run. It is limited by time, so we're talking about short executions of up to 15 minutes, which is, in my opinion, not that short. And then finally, they run on demand. So that means that when you don't use Lambda, your Lambda function is not running, and you only are going to be billed when your function is running, and it will run on demand when it gets invoked, which is a huge shift from Amazon EC2. Finally, the scaling is automated. If you need more Lambda functions, occurrences, and the concurrency, then automatically AWS will provision for you more Lambda functions. Magical. We'll see this in the hands-on. So, benefits of Lambda, I'm sure you see many. First of all, the pricing is super easy. You're going to pay for the number of requests Lambda receives, so the number of invocations, and your compute time, so how long Lambda was running for. There is a very generous free tier on Lambda, which is 1 million Lambda requests and 400,000 gigabyte seconds of compute time. It is also integrated with so many AWS services, as we'll see. We can use a lot of different programming languages on Lambda, so we're quite free. And there's very easy monitoring integrations with CloudWatch. Finally, if you wanted to provision more resources per function, you can provision up to 10 gigabytes of RAM per function, which is a lot. And by the way, you need to know this, if you increase the RAM of your function, then it will also improve the quality and performance of your CPU and network. So, now let's talk about the language support for Lambda. We have Node.js for JavaScript, Python, Java, which is Java 8 compatible or Java 11, C# for .NET Core, Golang, C# for PowerShell, Ruby, and you can write pretty much any language for Lambda thanks to the custom runtime API, which is community supported. And for example, if you want to run Rust language functions on Lambda, it is possible thanks to an open source project. So Lambda has a lot of language support, and it also has support for the Lambda container image. So this Lambda container image is quite special. The container image itself must implement the Lambda runtime API, so it's not any container image that can run on Lambda. Then needs to be some prerequisites about how that container image is built. And then ECS and Fargate is going still to be preferred for running arbitrary Docker images. So at the exam, if they ask you to run a container on Lambda, unless that container does implement the Lambda runtime API, you will want to run that container on ECS ECS or Fargate. Now, I said that Lambda was integrated with so many AWS services, so I'll give you a few and some idea of how they're integrated. And in this course, we will see some of these integrations. So API Gateway is to create a REST API, and they will invoke our Lambda functions. Kinesis will be using Lambda to do some data transformations on the fly. DynamoDB will be used to create some triggers, so whenever something happens in our database, a Lambda function will be triggered. Amazon S3, we've seen it already. A Lambda function would be triggered anytime, for example, a file is created in S3. CloudFront, this will be Lambda at Edge, and I have a lecture dedicated to this in this section. CloudWatch Events or Event Bridge, this is whenever things happen in our infrastructure on AWS and we want to be able to react to things. For example, say we have a code pipeline, state changes, and we want to do some automations based on it, we can use a Lambda function. CloudWatch Logs, to stream these logs wherever you want. SNS, to react to notifications in your SNS topics. SQS, to process messages from your SQS queues. And finally, Cognito, to react to whenever, for example, a user logs in to your database. So these are just the main ones. There are tons of Lambda integrations. And so I want to show you a very good example here, which is a serverless thumbnail creation. So let's say we have an S3 bucket and we want to create thumbnails on the fly. So there will be an event, which is that the new image will be uploaded in Amazon S3. This will trigger through an S3 event notification a Lambda function. In that Lambda function, we'll have code to generate a thumbnail. That thumbnail may be pushed and uploaded into another S3 bucket or the same S3 bucket, which would be a smaller version of that image. And also, our Lambda function may want to insert some data into DynamoDB around some metadata for the image, for example, the image name, size, creation date, etc., etc. And so thanks to Lambda, we've automated and had a reactive architecture to the event of new images being created in S3. Another example that's extremely popular is a serverless cron job. So cron is a way on your EC2 instances, for example, to generate jobs every 5 minutes or every Monday at 10 a.m., etc., etc. But you need to run cron on a virtual server, so an EC2 instance and so on. And so while your instance is not running, or at least your crons are not doing anything, then your instance time is wasted. And so as such, you can create a CloudWatch event rule or an event bridge rule that will be triggered every 1 hour. And every 1 hour, it will be integrated with a Lambda function that will perform your task. So this is a way to create a serverless cron, because in this example, CloudWatch events is serverless and Lambda functions are serverless too. Now let's take an example at the Lambda pricing. So you can find all the information on this website in case the information here is outdated, but it will give you an example of how that works. So you pay per calls. The first 1 million requests are free, and then you're going to pay 20 cents per extra 1 million requests. So that makes a very, very cheap request. Then you're going to pay per duration in increments of 100 milliseconds. So you get the first 400,000 gigabyte seconds of compute time per month if for free. And then what that means, this gigabyte seconds, is that it means you get 400,000 seconds of execution if the function has 1 gigabyte of RAM. That means you get 8 times as more seconds if the function has 8 times as less RAM, so 128 megabytes of RAM. And after that, you're going to pay $1 for 600,000 gigabyte seconds. So to be honest, you can make the math. It's usually very, very cheap to run your code on Lambda. So it's a very popular option to create your applications. So that's it. Now let's go into the hands-on to get a feeling of how Lambda works. Okay, so we're going to practice using the Lambda service. And when you go in Lambda, you may end up on this screen, but there's another screen I really like. And so if you're in your URL, you replace /discover by /begin, you may end up on this screen, which I really like because it has an educational value I want to show you. So Lambda is here to help you run code without thinking about servers, and this makes it a truly serverless service. So the idea is that we can use any type of programming language we want, for example, .NET Core, Go, Java, Node.js, Python, Ruby, or any custom runtime if you want to have a runtime provided by an open source project. For example, the Lambda Rust runtime is possible. And so from this code, you will have it written, uploaded into the Lambda console, and then AWS Lambda will run the code for you. So let's take a very simple code. For example, Python with a Lambda handler is going to print the event and then say return hello from Lambda. So let's click on run, and we get hello from Lambda. So that means that the Lambda function just ran the code that we have provided right here. Very simple, right? Next, how does Lambda functions get invoked? So we can click on the run button, obviously, but also we can have Lambda respond to events. And this is what I want to show you. I think it's really cool. So as we can see, events can come from various sources. For example, in this one, this is streaming analytics. And so as the streaming analytics is sending events into a Lambda function, the Lambda function is returning hello from Lambda, hello from Lambda, hello from Lambda, and so on. But it's not just the streaming analytics. If you click on the phone right here, it's going to send a message into a mobile IoT backend. And this IoT backend will also invoke our Lambda function. Same for if we take a photo and upload it into an S3 bucket for data processing, then the Lambda function will be invoked. But the cool thing is that if you start clicking a lot on one of these sources, you can see on the right-hand side, we have more cogwheels. So as the left-hand side flow and invocations of Lambda scales, then the number of Lambda invocations and concurrent Lambda functions running will be scaling as well. So it's really cool because that means that as we have more load, automatically Lambda will scale with our load. And that is a whole power of using Lambda as a compute platform, and this is why Lambda is serverless and it scales really well. So if we go in here, as we can see, as the Lambda function is invoked, we get more invocations over time, and the cost remains 0 because there's a free tier. And as soon as we will pass 1 million invocations, then the Lambda function will start incurring some charges. So if we go in there and start having over 1 million invocations, here we go. Now we're getting some sense. As you can see, we are at almost 2 million invocations, and we have only 14 cents as a cost. So it's very, very, very cost efficient to have a Lambda function and to run some workload at scale. So as you can see, you can play around and seeing that the more you have invocations, the more the cost goes, but it's really, really controlled. And Lambda can be quite a cost saving mechanism if you use it at scale. So this is just for the introduction to Lambda. So if I click on create a function, I can choose between 3 options. And I'm going to choose to use a blueprint for this one. And it's going to be the hello world function. So I'm just going to search by hello world. And then I will choose the Python version. So Python 3.10 in this example, but this could be a different version for you as long as it's Python. Next, for the function name, we're going to enter demo minus lambda. And then we're going to create a new role with basic Lambda permissions. This is going to be the IAM role of our Lambda function. Then we can have a look at the function code. So this is what a Lambda function looks like. So we have a Lambda handler. This is the function that actually handles the event of invoking our Lambda function. And right now it just prints a bunch of values and returns the key one. So we'll have a look at this in details when we test our function. So when you're ready, just click on create function. Okay, so my function is created. And as we can see, the code has the code source in here. And if I click on lambda function.py and open it, we can see that the function code we had from before is now loaded into this code editor. So why don't we go ahead and test this function? So I'm going to click on test, and we need to create a new test event, which is a hello world event, which contains key 1, value 1, key 2, value 2, key 3, value 3 as a JSON document. So I'll call this one demo event and click on create. So now the demo event was successfully saved. So if I click on test now, it was going to run the demo event, and the response is value 1. The function log is that value 1 equals value 1, value 2 equals value 2, value 3 equals value 3, which is just a result of this 3 print statements. And finally, the response value is value 1. again, due to this line of code. So it may not look like much, but from a programmer's perspective, as you can see, you had just some code and it was uploaded into Lambda and then it was run by Lambda very quickly. So this is a huge improvement if you're a developer, as you can see, to deploy the code and have it run. But on top of it, it runs seamlessly and it will scale automatically and it is fully serverless. Okay, we didn't deploy any servers. Now in terms of build duration, so if you go in here and scroll down, then as you can see, the duration was 2.32 millisecond. We've been billed for 3 milliseconds of execution. And here's the memory size that we've provisioned and the one that was used and how much the init was, because this is the first time that we use our Lambda function. Now, if I run it again, if I go back to my function, and run this one again, as we can see now, the function duration was 1.33 millisecond. And on the right-hand side, there was no initiation because my Lambda function was ready to be used. Okay, so that's one way of doing things. Now, the other thing I want to show you is that from this Lambda function, we're able to configure it. So if I go into general configuration, we get some of the most important settings. The first one is around memory. So we can have the memory from anywhere between 128 megabytes up to 10,240 megabytes of memory. Obviously, if you have more memory, you're going to get billed more. In terms of timeouts, we can go anywhere between 3 seconds or 5 seconds all the way to, as you can see, 15 minutes. So the maximum timeout is 15 minutes, but you want to make sure that you only use the function for the time that you think is going to be used for. And then the execution role is the one that was created by Lambda in the beginning. Okay, so those are some of the most important settings, okay? And the other thing we can look at is monitoring. So in monitoring, we're able to see what is going on with the Lambda function. So how many times it was invoked. So here one time, how long it lasted, whether or not there was errors or successes, and so on. So it could be quite helpful, but we have integration with CloudWatch metrics and also CloudWatch logs. So right now we have nothing, but we could look at the CloudWatch logs right now when the function runs. So to do so, just refresh on the right-hand side the recent invocations, and we can see that there's a log stream right here. So if I click on it, I am taken directly into the CloudWatch logs, and we can see that on the CloudWatch logs, we have all the logs of the invocation of this Lambda function. And this is within a log group called AWS Lambda, Demo Lambda, and Demo Lambda is the name of my Lambda function within my region, obviously. And we have one log stream right here. So we get all the logs into Lambdas. And other things you can try is to modify the code. For example, if we take this code, we go to the Lambda function, and I will comment this line of code by adding a hashtag and uncomment this one. This is going to raise an exception. So to do so, I need to first deploy the changes by clicking on deploy. Now the changes have been deployed, and now I can test my function. And in this type, we get a execution result, which is an error, where something went wrong. Type is exception, as we can see, something went wrong, which was triggered by this code, line of code right here. So any type of errors also will be reported by Lambda, and you could look into CloudWatch logs to understand as well where the log of the error happens. So if I go back into CloudWatch logs, there's a second log stream right. here, which I'm going to open, and we get this exception right here. So it's possible for us to go back as well to the logs of the exception within CloudWatch logs to understand the root cause of the issue. So fairly easy. Now, if you want to make the function run again, fine. You just reverse what you did and you click on test. And again, now this time, this Lambda execution function will work. So some of the last things we may want to check out is the fact that in here, the runtime settings, we're running Python 3.7 in this example, but you may get an updated version maybe on your end. And the handler is lambda function.lambda handler, which is saying to look at the lambda function.py file and the function name lambda handler. So if we go up, we can see the function name is lambda underscore function.py. And within it, we have the lambda underscore handler function. So this is why it knew to invoke this function particularly. Also, we have written to CloudWatch logs, and the reason we were able to do so is that if we go into the configuration of our lambda and go to the permissions tabs, we have a role name called demo lambda role that was created for us by the lambda console. And if you look at the policy itself, we can see within the policy summary that we have access to write to CloudWatch logs, which is something you can also see right here by resource summary, that CloudWatch log has 3 actions on 2 resources, which allow us to create log stream and log groups and also send the logs to CloudWatch logs. So this is the whole idea behind this permissions tabs right here. So that's it for this lecture. I hope you liked it. And if you are in the Certified Developer course on AWS, then get ready for an extra few hours of content on Lambda. And if you're not, well, this is enough for your exam. I hope you liked it, and I will see you in the next lecture. So you need to know a few Lambda limits before going into the exam, because the exam likes to see if you know these limits, and these limits are per region. So we have some execution limits, and then we'll have some deployment limits. So execution is that the memory allocation is between 128 megabytes to 10 gigabytes, and this is in 1 megabytes increments. And when we increase the memory, then we have more vCPU. You understand this now. The maximum execution time is 900 seconds, which is 15 minutes. So anything above that is not a good use case for Lambda. Environment variables, we can only have up to 4 kilobytes of environment variables, so a limited amount of space. But there is a temp space if you want to pull in some big files while we create our Lambda function. And so this is disk capacity in the /tmp folder, and we have up to 10 gigabytes there. We can have up to 1,000 concurrent executions of our Lambda functions. This can be increased as well if we do a request, okay? But it's good to use reserved concurrency early on. Finally, for deployments, the max size for your compressed zip is 50. Uncompressed, it is 250 megabytes. So anything above that, for example, big files, you should use the /tmp space instead. So as I said, in case you need to have big files at startup, please use that directory. And finally, again, the environment variables is 4 kilobytes. So once you know all these limits, when the exam will ask you a few questions, such as, we need 30 gigabytes of RAM, or we need 30 minutes of execution time, or we need a big file of 3 gigabytes, then you will know that Lambda is not the right way to run this workload. I hope that was helpful, and I will see you in the next lecture. So now let's talk about Lambda Snap Start. So this is a feature of Lambda that helps you improve your Lambda function performance up to 10x at no extra cost for your Lambda functions that are running on Java 11 or above. So let's understand how and why. So your Lambda invocation have several lifecycle phases, and if snap start is disabled, and you have, again, remember, a Lambda function that is running on Java, then whenever your Lambda function is invoked, your Java code is going to be initialized, then invoked, and then there's going to be a shutdown. But when you enable snap start, then the function is going to be invoked from a pre-initialized state. That means there is no function initialization from scratch. So when you enable snap start, then your Lambda function running Java again is invoked, but the function is pre-initialized, and so this init phase, which can last a very long time in Java, is gone, and you go straight into the invoke phase and then the shutdown phase. So this is a feature that is completely free. And how does it work? Well, whenever you publish a new Lambda version, then Lambda is going to initialize your function. So this init phase is going to be done ahead of time. Then a snapshot of the memory and the disk state of your initialized function is going to be taken. And finally, this snapshot is going to be cached for low latency access, which allow your function to have what's called a snap start, a rapid start. So that's it for this lecture. I hope you liked it, and I will see you in the next lecture. So let's talk about customization at the edge. So what does it mean? Well, we know we deploy our functions and our applications in a specific region, but sometimes using, for example, CloudFront, we have the edge locations that are distributing our content. And sometimes the modern applications require to execute some sort of logic at the edge before reaching the application itself. So these are called edge functions, and this is a piece of code that you write and that you will attach to your CloudFront distributions. The idea is that you want to run these functions close to users in order to minimize latency in some cases. So CloudFront has two kinds of functions. You have the CloudFront functions and Lambda at edge. The idea will be to be able to understand when they are required and their differences, and we'll do this in this lecture. But using the edge functions, you don't have to manage any servers. These edge functions are deployed globally, and the use cases of them, for example, will be to customize the CDN content coming out of CloudFront. Also, you only pay for what you use, and it is fully serverless. So now let's have a deeper look into these things, the use cases. The first one is around website security and privacy. Then we have dynamic web applications at the edge. We can do search engine optimization, SEO. We can do intelligent routing across origins and data center, bot mitigation at the edge, real-time image transformation at the edge, A/B testing, user authentication and authorization, user prioritization, user tracking and analytics, and so on. So this is a lot of different customizations we can have using CloudFront functions and Lambda at edge. So now let's discuss what CloudFront functions are used for and how they work. So this is what a typical request into CloudFront looks like. So the client will do a request into CloudFront, and this is called a viewer request because the client views it. Then CloudFront will do an origin request into your origin server. The server will reply to CloudFront, so we have an origin response. And finally, CloudFront sends that response to the client, so we have a viewer response. Now, CloudFront functions are lightweight functions written in JavaScript, and they modify the viewer request and response. They're used for high-scale, latency-sensitive CDN customizations, which gives you sub-millisecond startup types and a scale of millions of requests per second. As I said, they're used to change viewer request and responses only. So the viewer request is after CloudFront receives a request from a viewer, you can modify this, or the viewer response is to before CloudFront forwards the response back to the viewer. It's a native feature of CloudFront, and the entire code is managed from within CloudFront directly. Remember, CloudFront functions, high performance, high scale, only for the viewer request and response. Now, Lambda at edge is a bit more, so you can modify all of them. So these are functions written in Node.js or Python, and you scale to thousands of requests per second, and it's used to change CloudFront request and response, multiple ones, so all of them actually, the viewer request and the origin request, which is before CloudFront forwards the request to the origin. You also have the origin response, which is after CloudFront receives the response from the origin, and the viewer response, which is before CloudFront forwards the response back to the viewer. You author your function in one region, which is US East 1, which is the same region where you manage your CloudFront distributions. And then CloudFront is going to replicate this function to all of its locations. So we have a table here to differentiate between CloudFront functions and Lambda at edge. So one notable difference is the runtime support. Of course, JavaScript only for CloudFront functions, and then Node.js and Python for Lambda at edge. The scale is really, really high scale for CloudFront functions. We're talking about millions of requests per second versus thousands for Lambda at edge. Now, where the trigger is happening is a big difference. So Lambda at edge has impact on both the viewer request and the origin, whereas the CloudFront functions is only on the viewer. And very important, the max execution time is less than 1 millisecond for CloudFront functions. So they're very, very quick and simple functions. Whereas for Lambda at edge, you can get up to 5 to 10 seconds. So you can perform a lot of logic in these functions. The rest, you can have a look, okay? Now, in terms of use cases, CloudFront function is going to be for cache key normalization. So to transform, for example, the request attributes to create an optimal cache key. Header manipulation to insert, modify, or delete HTTP headers in the request or response, or to do URL rewrites or redirects, or to request auth and authorization to create and validate JW2 tokens to allow or deny requests. So all these things can be executed in less than 1 millisecond, whereas Lambda at edge has a longer execution time. It could be up to 10 seconds, for example. You have adjustable CPU and memory, so you can load a lot of libraries, and your code can depend their on third-party libraries, such as the SDK if you wanted to access other AWS services. You also have network access to external services for processing the data, so you can really perform some big integrations. And Lambda at Edge gives you file system access or access to the body itself of the HTTP request, so you can do some more customizations. So hopefully that helps you. I hope you liked this lecture, and I will see you in the next lecture. Now let's talk about some networking fundamentals for Lambda. So by default, when you launch Lambda functions, they're launched outside of your own VPC. They're actually launched in an AWS-owned VPC. So you do not have access to resources within your VPC. So if you launch an RDS database, an Elasticache cache, or an internal load balancer, then your Lambda function will not have access to it. So this is the default Lambda deployment. It will work if it needs to access any public API on the internet. It will work if it needs to access DynamoDB, because DynamoDB is a public resource on the AWS cloud. But if you have a private RDS database, the connectivity will not be working. You know where this is getting to. We need to actually launch your Lambda function in your VPC. So this is an option you can do, and you need to specify, therefore, your VPC ID, the subnets you want to launch in, and attach a security group to your Lambda function. Then your Lambda will have an elastic network interface in your subnets, and therefore it will be able to access your Amazon RDS, for example, running in your VPC. So this is how we launch a Lambda function in your private subnets. And therefore you will have private connectivity to anything in your VPC, which is good. So a major use case of Lambda in a VPC is to use Lambda with the RDS proxy. So again, we have an RDS database in a private subnet, but we have our Lambda functions and they access it directly. But the problem is that if they access your RDS database directly, it's going to be a huge problem, because if you have many Lambda functions appearing and disappearing over time, then you may have too many open connections under high load on your RDS database, and it will lead to timeouts and issues. So instead, what you would do is to launch an RDS proxy. And this proxy was going to pool connection and connect with less connections into your RDS database instance. So your Lambda functions now connect to the RDS proxy, which connects to the RDS database instance, and you've solved your architectural problems. So 3 benefits of the RDS proxy is that number 1, it improves scalability by pooling and sharing database connections. Also, in case of failover, this will improve the availability by reducing by 66% the failover time and preserving connections. This is for RDS and Aurora, of course. And also, if you wanted to enforce IAM authentication, you could enforce it at the RDS proxy level and store these details in Secrets Manager. So for this to work, for the Lambda functions to connect to your RDS proxy, you need to launch your Lambda function. In your VPC. That makes sense because the RDS proxy is never publicly accessible, and therefore if you launch your Lambda functions publicly, you will have no network connectivity to your RDS proxy because it is never public. So if you understand this, you will be able to solve 1 or 2 questions at the exam. Okay, that's it. I hope you liked it, and I will see you in the next lecture. So is there a tight integration from RDS, Nora, and Lambda? Well, we can actually invoke Lambda functions from within your database instance in some cases, and this would allow you to actually process data events happening from within your database. So this is supported, for example, by RDS for Postgres and Aurora MySQL. And the idea is that, for example, a user is going to insert an event data into your table, your registration table, and RDS will be set up to directly invoke your Lambda function. Your Lambda function may send a welcome email to your user, and then the user will receive it. So this is something that you have to set up from within the database by connecting to it. This is not something that you set up from the AWS console. And when you do that, the RDS instance is the one invoking your Lambda function. And so therefore, you must sure to have allowed the abound traffic from the RDS database instance to the Lambda function through whatever way, either because your Lambda is on the public internet, so we can use the invoke, or a NAT gateway, or VPC endpoints, and so on. But network connectivity is important. On top of it, of course, because your RDS database instance is going to invoke your Lambda function, then you must have the required permissions to invoke the Lambda function. And so you make sure that your database instance has a proper IAM policy. This is completely different from using the RDS event notifications. So these notifications are happening within AWS, and they're notifications that tell you information about the database instance itself. For example, when it was created, when it was started, and so on. And you don't have any information of the data happening within your database. So don't fall for this trap. So you can subscribe, for example, to events about your database instance, your database snapshots, your parameter group, your security group, your proxy, or the custom engine version, but you're not going to get information about the data within your database. You get near real-time events, so up to 5 minutes of delivery, and then you can send these to SNS, or you can also intercept them in EventBridge. So from SNS, we can, for example, send them to an SQSQ or a Lambda function, and from EventBridge, you can have so many different destinations, including, for example, a Lambda function. But remember, you do not get information about the data events themselves. You have to use the previous methodology as I've shown you from before. Okay, that's it for this lecture. I hope you liked it, and I will see you in the next lecture.